Hello, Brian Miller-Hicks. I'm an engineering geologist. I have been an engineering geologist for decades. It's a good field, it's a good career, it's a good subcategory of geology. It has to do with, as I practiced it, with construction. So, an architect, an engineer, a designer, developer, builder wants to build something on a piece of ground. They would hire somebody like me to go investigate first. So what we're looking for is conditions that could impact construction, like shallow groundwater, earthquake faults, landslides, clays, etc. So it's an important field. It's practiced rigorously here in California. So let me explain what it's all about. This first slide, as you see, is kind of a mess. This is a roadway in San Diego on Mount Soledad, which is near La Jolla. And this is a landslide which occurred in 2007. Which took out, as you can see, took out the roadway. A lot of damage. This happened in an area that's prone to landslides. There had been old landslides existing in this area before, which unfortunately were not repaired correctly in the 60s. Basically, for something like this, what you need to do is excavate the bad stuff out and rebuild the slope and rebuild the roadway. And that's what was done in this case. Um, so engineering geology is sometimes called applied geology. It means basically the same thing. And as you can see, it's all about the ground we live on. So let's go to, let me explain that this is PowerPoint was part of an engineering geology course I taught in 2002 at San Diego State. And the textbook, as you can see, is Practical Engineering Geology by Steve Hencher. So we do talk about environment in the sense in its relationship with engineering geology by means of addressing environmental conditions which can affect construction. At the same time, construction can sometimes impact the environment. So let's go through this. Um, Here we have Borrego Springs, which is near San Diego. It's a desert area, as you can see. We have an array of solar panels, large solar panels to generate energy. Um, every time a solar panel is built, you might consider that as a building, as construction. So an engineering geologist has to assess soil conditions and present the data to engineers for the design of the panels and the structures. So there's a link here between engineering geology, environment, and energy in this case. Here's another um, energy generating facility, windmill farm, Palm Springs. Again, I use this to illustrate that structures are necessary for us to obtain energy by means of wind. And these structures have to be, the foundation conditions for these structures have to be assessed before construction actually commences. Here's something from Europe. It's sort of unusual. We haven't gotten to the point yet where sea level rise is impacting us quite as severely as the city of Venice in Italy, for example. Here you see they've actually turned a problem into a tourist activity where they give tourists nice, colorful rubber boots, orange, green, yellow, and they can go ahead and splash in the water when the tourist attractions, plazas, etc., get flooded in by rising sea levels. Here's how they have dealt with the problem. They have engineered and constructed these massive, massive flood protection gates which open and close according to the inflow and outflow of water. So, but first, again, an engineering geologist or team of engineering geologists had to go in and assess conditions, muddy bottom, I assume, of the Venice bays and streams and delta type environment. So, as you can imagine, these are pretty tricky conditions to try to assess and tricky conditions to actually construct something this massive. Solana Beach seawall, again, closer to home. This is the San Diego area. Here we have, um, of course, structures that were built to protect the buildings that you see at the top of the bluffs. The bluffs are made of sandstone, Eocene in age primarily, um, which are very erodible, subject to erosion by large waves, storm action, wind, salt, etc. So the temporary solution is to build what we call seawalls, which you can see really aren't that attractive, but they serve the purpose, at least temporarily, until the ocean comes in, decides to undermine underneath these seawalls, then there can be problems. So as you can imagine, the data we're looking for in cases like this is to see how thick the beach sand is, how deep it is to bedrock. You're going to find these walls on top of and embedded in solid bedrock down below the beach sands. Here's some situation where seawalls were constructed in accordance with the issue of earthquakes in Japan. The scientists and engineers over there thought the seawall was high enough, something like 25 feet or so in height, to block any tsunami from large earthquake event. Unfortunately, as you can see, the earthquake was so powerful and the tsunami was so large that it overtopped this very high wall. Adding to the issue, to the problem, was the fact that not only did these huge tsunami seismic wave come in, but the portions of the coastline actually sank a few feet. So that had the effect of lowering the height of the seawall, causing problems, as you can imagine. Again, engineering geologists were involved in looking at foundation conditions, bedrock conditions, and also, importantly, significantly analyzing um, various earthquake scenarios, trying to determine the actual energy that would be generated by large earthquakes and how these seismic waves, vibrations from earthquakes, would affect civil structures and generate seismic waves. Earthquake science is an offshoot of geology and engineering geology, and it's quite a specialized field. A lot of very smart people have set up seismometers to register waves from earthquakes all around the world through time and are working hard to make designs and pose various scenarios to help protect us from earthquake damage. Engineering geologists also contribute to seismology by locating and mapping earthquake faults, giving a lot of that very vital information to seismologists and others. When you map a fault and look at a fault, you have to determine whether it's active or inactive. And there are certain criteria for that. I'll get in more into detail on that on a later PowerPoint presentation. So, is all ground solid? Is it all bedrock? Is it all able to bear the weight of structures or excavation activities without problems? No, not all of it's very solid. So engineering geology, in part, is not only looking at natural conditions, but looking at ways of improving the stability and strength of existing natural materials. So to get down to basics, of course, we have soil classified with texture and size. Clay, of course, is the finest grained particle, microscopic in size. Silt is the next largest, a little bit larger in size. Sand, of course, everybody's pretty familiar with, is yet more um, coarse in size. And then you go to gravel. So clay is not especially really good to build on because it's so fine grained, it's not very strong in a wet condition especially. And when it's wetted, some clays can actually expand, which is not a good idea if you're sitting or building on top of clay. Here's an example of what happens when you found a building on top of clay without mitigating it, without doing something to improve the strength of the material, the clay material. So this gentleman is looking at wall damage from expansive clays. You can see this quite significant cracking through the brick. Notice how it follows the joints between the bricks, which are weak points. The mortar, if you will, between each brick is not as strong as the brick itself. So here's what happens. Clays are layered soils. They're formed of sheets or layers of primarily silicate molecules, um, various different types of clay. When a clay is dry, it's unexpanded, but then you introduce water, and the water gets in between these clay layers like filling of a sandwich, forces each layer apart, and the general effect of that is expansion in volume and also weakening of strength of the material. So the clay expands, and as it expands, it pushes up on whatever is sitting on top of it and causes distortion, damage, breakage, all sorts of nasty effects. By the way, I forgot to mention at the outset, but this is part one of engineering geology, so I'll be doing part two, obviously, subsequently, so that I'm not going on too long with these. Here's some bedrock, sandstone. What is sandstone but material which started out as sand, being laid down primarily in a watery environment, in this case a nearshore marine or beach type environment. So as the sand is deposited by water through time, age, and compaction and cementation, the sand becomes sandstone. So again, through time, deep burial, and the introduction of cements between and among all the sand grains that solidifies and turns that once loose sediment into hard sandstone. Generally speaking, sandstone is pretty strong. It has good foundation characteristics. The things you have to watch for with sandstone exposures is that sometimes it has low cohesion or stick to itiveness, so that individual grains can be loosened by wind and water and rain and can start sliding down a very steep near vertical face like this. This is Torrey Sandstone picture taken at Torrey Pines Reserve, which is fairly notorious for failures of large sections of the sandstone bluffs. So if you're an engineering geologist, you probably would not recommend that somebody build their house or cabin or cabana at the base of this bluff. So how do we get information about ground conditions? Well, we have to dig, got to drill, got to use backhoes, drills, etc., to get to the bottom, no pun intended, of every situation. This is an instrument that some people know how to use. Other people haven't used one in quite a while. It's, of course, the basic shovel, and you start digging with this piece of metal to try to get some information from the shallow near surface layers. Can't dig very deep with a shovel. I mean, you can, but it takes a lot of time, obviously. Here's a method of getting information from much deeper depths than you would with a shovel and under some difficult conditions for getting information. So this is a job I was on in San Diego Bay at the naval station where one of these dry dock areas had blown out and flooded, so they had to reconstruct it. So we had to find out how deep the water was, how deep the very soft, loose clays and silts were at the bottom of the bay, and where bedrock was. So we had to bring in a truck on a barge. This is actually this wooden surface is actually the deck of a barge. So the barge placed itself to where we started drilling off the edge of the barge into and through the water and into the bottom sediments. So we had to go, in this case, close to 100 feet using what we call hollow stem augers, which drill down like corkscrews. Then we could slide samplers down the hollow space in the center of the auger and then pull up samples as we advance the boring deeper and deeper into the water and the muck down below. So it was vital, as you may imagine, to get information on the texture, strength, and depth of all these materials so they could rebuild this dry dock. I was out there a couple, 3 days. It was kind of fun going out there to the bay and standing on a barge and doing the work. Okay, so I mentioned sampling. So this is one kind of sample we extract from drilling with a truck rig like you see here, which is the truck rig on the bay that we were using. Uh, Essentially, it's fairly simple. You use a hollow metal tube, which you then drive into the sediment with hammer blows, hydraulic blows. The convention is a 140-pound hammer driving 30 inches. And the number of blows it takes to go a foot into the material is what we call a blow count. So the higher the blow count, the more solid the material is. A material with a low blow count is soft and generally weak. Material with a high blow count is stronger and more solid. This looks like a clay material, so it probably didn't have a really high blow count. And of course, here is a machine which many of us have seen. It's very, very useful, practical. It digs with power. And the good thing about this is a geologist, an engineering geologist, can not only see the material as it's coming out and take samples of it, albeit the samples will be excavated, broken up material, but he or she can also get into the test pit after it's been dug with safety considerations in mind. Never get into a backhoe pit deeper than 5 feet without some support on the side walls. So the advantage of getting into the pit, though, is to look at the stratigraphy, the layering of materials, see where it changes from one type of material, maybe a silt, to maybe clay 2 feet down, to maybe bedrock 4 feet down. So you get a really good picture of stratigraphy. Backhoe excavations are especially useful when you're looking for earthquake faults. This is a deeper, more expensive, and um, uh, method of getting information on deep sediments and geologic structure. This is used primarily by the oil industry to find buried structures that may contain traps where they can find oil. I became familiar with these methods when I worked in West Texas in the 70s in the Permian Basin. What's going on here is we have a truck going along a predetermined surveyed line. The truck sends energy by means of a vibrating pad, which vibrates the top layer of soil, sends vibrations or seismic waves down deeper into the substrate. These vibrations or waves can bounce or deflect off different types of material, such as granite. So the waves will go through the sediment at a certain speed and then bounce off the granite and come up to the surface to be picked up by these devices called geophones. So all that data is then transmitted to computer trucks, boiled into give you a three-dimensional picture of subsurface structure where you can actually see faults and folds and other types of structure based on the reflection and deflection and diffraction of various energy waves being transmitted by the vibrator truck. So I'm going to stop there for part one, and we'll go on part two when I get back to it.